So reactions of acids and bases, we've talked about these briefly in chapter, I think it was 7. If you have an acid, that pointer, there it is. If you have an acid and a base that react together, what we learned earlier was to treat this as a double replacement reaction and swap partners. And so the H and the OH go together and form water. The potassium ion and the chloride ion go together and form a salt. So generally we see acid-base reactions giving us water and salt. And what we mean by salt is just an ionic compound. So the net ionic equation for this acid-base neutralization is just going to be hydrogen ion plus hydroxide ion gives us water. Because the potassium and the chloride are soluble in the end and they're soluble in here. And so they're just spectators watching what's happening. When we have an acid that reacts with a carbonate or a bicarbonate, this is the reaction of hydrochloric acid with sodium hydrogen carbonate. That's baking soda. What we see is that water is produced, but also gaseous carbon dioxide, and then a salt. In this case, it is actually what we call table salt, sodium chloride. So this is a neutralization reaction because the acid is neutralized, but it's also a gas evolution reaction because a gas is evolved. So some chemical reactions can fit more than one classification. Let's write a molecular equation for the reaction that occurs between aqueous phosphoric acid and aqueous sodium hydroxide. And we're given a hint here. H3PO4 is what's called a triprotic acid. Remember we said that a hydrogen ion is just a proton. And we always write those ionizable hydrogens at the beginning of an acid's formula. So H3 means there are 3 hydrogen ions that can be released. So it will take 3 moles of hydroxide to neutralize those. So to write this equation, we'll start off with our reactants. So we've got H3PO4, and we're told that's aqueous, and sodium hydroxide, and that is aqueous. So here we have an acid and a base. We're going to end up with water and a salt. I think the best approach here is to look at this as a double replacement, take the ions apart from each other, and then swap partners. So if we look at this, what we've learned is that this is hydrogen ions and phosphate ions. So H plus and PO4, and the charge on that is 3 minus. That's something you should memorize, but you can also figure out based on the fact that there's 3 hydrogen ions there. And then we've got sodium ion and hydroxide ion. And what we're going to do is we're going to swap the partners. We're going to put sodium and phosphate together, hydrogen and hydroxide together. When the hydrogen and the hydroxide ions get together, they form water. Sometimes if you're not really awake yet, you put those together as HOH, and then you say, that looks weird. Oh yeah, that's water, H2O. And we're not going to say that water is aqueous because that would mean it's dissolved in water, right? Water at room temperature is a liquid. And the other pairing here, always the positive ion first and then the negative. Good news first and then the bad news, I guess. Positive and negative. So we've got sodium and we've got phosphate. The charges are important because they tell us how to put the ions together. So the charge of 3 minus on the phosphate and the charge of +1 on the sodium tells me I need 3 sodiums with the phosphate so that I can have a neutral compound. And the common thing that students prefer to do is just do this crisscross thing, and that's how you get Na3PO4. I don't need parentheses around this phosphate because there's only one. I don't need parentheses around the sodium because it's a monatomic ion. We only use parentheses on polyatomic ions. So now I've got all of my reactants and products, and I need to balance the equation, right? The phosphate ion stayed intact, so we can balance that as a unit if we like. If you want to take it apart and look at phosphorus and oxygen separately, you can do that too. So there's one phosphate ion here, and there's one phosphate ion there. There's hydrogens and oxygens all over the place, so I like to ignore those till the end. Here's a sodium. We have one sodium on the left side and 3 sodiums on the right side. So that means I'm going to put a 3 in front of the sodium hydroxide. So I've got 3 sodiums on both sides. Now let's count up all of those hydrogens. So I've got 3 hydrogens here, and I've got 3 times 1, 3 hydrogens there. So that's a total of 6. Over here I have 2 hydrogens. So if I say I've got 3 water molecules, then I'll have 6 hydrogens. I've got 3 oxygens in the sodium hydroxide. The 4 oxygens here go with the 4 oxygens over there, so I can ignore them. 3 oxygens and then 3 oxygens, and so there's my balanced chemical equation, the molecular equation. Any questions? So what this means when it says 1 mole requires 3 moles, that's the ratio. 1 mole of phosphoric acid would require 3 moles of sodium hydroxide to neutralize it. So acids can dissolve many metals. Sometimes in spy movies they show, the spies in jail, and they've got some little capsule of acid, and they dissolve the bars of the jail cell window, and they get out. Yeah, that doesn't really work that fast. But acids can dissolve many metals. Here are some examples. Hydrochloric acid and magnesium. Okay, we did that one in class. We had the strip of magnesium, and we put it in the eudiometer, and we collected the hydrogen gas. Zinc metal can be dissolved with acid. Here's sulfuric acid, and zinc metal gives us hydrogen gas and a salt. Hydrochloric acid can dissolve iron, giving hydrogen gas and salt. But not all metals can be dissolved with acids. When acids do react with metals, they do so in a way that causes the metal to go into solution. So the metal is dissolved. It looks like it's disappearing, but it's not disappearing. It's just becoming an ion that is soluble. So this reaction that we did in class, we knew it was finished when the bubbling stopped, no more hydrogen being produced, and that strip of magnesium was completely gone. The magnesium became magnesium chloride, which is soluble, and so what used to be a solid metal is now dissolved ions. Which, seems kind of crazy. How can you put metal in what looks like water and have it disappear? But you put a teaspoon of sugar in water and stir it and it disappears, and we don't get freaked out by that, right? It's the same idea, it's just dissolving. Oftentimes these will produce hydrogen gas, these reactions. What's next? Acids can react with metal oxides. A metal oxide is really just a rusted metal. So hydrochloric acid with potassium oxide, we're going to get water and salt. And again, we can treat these as double replacement reactions. So the potassium and the chloride end up as the salt, and then the hydrogen and the oxygen become water. Here's hydrobromic acid with magnesium oxide, making water, and the other 2 ions become a salt. So let's write equations for these reactions. The reaction of hydrochloric acid with strontium metal. Well, we should know what the formula for hydrochloric acid is. So HCl, and that's aqueous. Strontium metal, well, the symbol for strontium is Sr, and metal, the symbols for metal, or the formulas for metal are just the element symbols. And that is a solid at room temperature. Mercury is the only one that's not. So this is reacting. So what's going to happen here? When metals react with acids, they're going to form a compound of the metal. The metal's going to form a compound with this ion. This is a single replacement reaction. I think of this as, so I've told you, I think that I consider the metals to be masculine. And hydrogen here is sort of acting like a guy. So here's hydrogen coming in with chlorine. Chlorine is a nonmetal. I think of the nonmetals as non-masculine or feminine. So here's hydrogen. He's all hot stuff because he came in with chloride. And she's just, drop dead gorgeous or whatever. And here's strontium. And so they're both going to the same party. Strontium came by himself. But during the course of the evening, as they get to know each other, chloride decides that strontium is cooler than hydrogen, and so she leaves with him. And hydrogen gets left going home by himself. Stuff like that can happen, right? Hopefully it never happens to you, unless you're strontium, and that might be good. Anyway, so the hydrogen's going to leave by himself, and the chloride's going to leave with strontium. Well, how do a metal and a nonmetal form a compound? They're ions, right? So what kind of an ion does strontium make? We have to look at the periodic table. What group is it in? Group 2. Makes a 2+ ion. So strontium is going to become an ion. Chloride is already an ion. Hydrogen's going to leave by himself. Hydrogen by himself has what formula? H2. And hydrogen is a gas at room temperature, so H2 gas. And then strontium and chloride, putting those two together, we look at the charges. You could do the crisscross thing if you want. Strontium chloride. Is that soluble or insoluble? How do we know? The table, yeah. So, Chem 3A, I didn't make you memorize the table. After you use it for a while, you start to remember some of it. The halides, iodide, bromide, chloride, form soluble compounds with only a couple of exceptions. This isn't one of the exceptions. This one's aqueous. So I'm going to erase my scribblings. What else do we need to do this equation? Balance it. So what do I need to add in here to balance it? A 2 in front of the HCl. That gives me the 2 hydrogens and 2 chlorides. For over here, 2 hydrogens, 2 chlorides, the strontium's fine. So I consider this to be a somewhat challenging type of question for a Chem 3A student. And I would only ask you a question like this for a metal that only forms one kind of ion. Because if you did this with something like iron, which can form a +2 or a +3, how do you know which one? You don't have the background to know. And in fact, even an experienced chemist might not know because there might not be enough details to tell you which one is going to be formed. Those could end up on a worksheet or a lab, in which case I will look at the answer, and if you're using any of the possible ions for that metal, I'll count that as correct. Let's look at reaction of hydroiodic acid with barium oxide. Hydroiodic, that's one of those binary acids. So high, very friendly. Barium oxide, ionic compound, so we need to look at the ions. So barium's in group 2A, it's got a +2 charge. Oxide, look, find it on the periodic table. Start with the noble gases, they have a charge of 0, count backwards, -1, -2. So oxygen has a 2- charge. So this is going to be BaO. Now, it's not actually telling us we have to include the state symbols, and it's not telling us what the state of that is, so we can be lazy and just not include them. How's that? So how do we predict what's going to happen here? Whenever you have to predict and you're not sure what to do with it, try just taking the ions apart and swapping partners. I don't think I was here for that, the lecture where we did that, or where you did that with my sub. So I was telling you how this is the guy and a girl going, and here's the guy going stag, and he ends up with the girl, and hydrogen goes home by himself. Here we have two couples going to a party, and during the course of the party, they decide they like the other person's partner better, and so they swap partners. So barium and iodide are going to leave together. Hydrogen and oxygen are going to leave together. So rewrite the formulas because you need those charges. And just like on formal invitations, it's always Mr. and Mrs., right? Not because men are more important or more valuable or anything. It's just tradition, right? Mr. and Mrs. So it's always the metal and then the non-metal, just because. Okay, so when I put these two together, the charges tell me that the formula is going to be BaI2. I need two of the iodides to balance the charge on that. This, we look at that and we're like, that looks strange somehow. But you can look at the charges here and still come up with the right answer. What do the charges tell us to do? 2 hydrogens and 1 oxygen. Oh, that's water. Cool. Okay. There's our formulas. Then we need to balance it. Two of the acid, right? 2 HI. So I got 2 hydrogens here, 2 hydrogens, 2 iodides, 2 iodides, 1 barium, 1 oxygen, 1 barium, 1 oxygen. Any questions? So base reactions. The important base reactions are those that occur with acids. So those are neutralization reactions. We already talked about those. The only other thing we're going to look at here is sodium hydroxide reacting with aluminum. Aluminum is one of very few metals that will dissolve in a base. So we can take sodium hydroxide, potassium hydroxide, something like that. Aluminum, and this has to be done in water because water becomes part of the compound that's formed. And we can actually dissolve the aluminum. This is very similar to, well, actually this is, one of the steps that we did when we made alum. We took aluminum powder and dissolved it. I think it's cooler when we use aluminum foil, but because that looks like something, right? But the aluminum dissolves. We used potassium hydroxide, but here it dissolves in sodium hydroxide as well. So I'm telling you about this. I'm not going to test you on that one, but I just want you to have heard about it.